Hi, I hope this is working. The primary objective of the stream and the series of streams is to get 1 minute. So, the primary objective first of this channel is to explore our skills, and it's sort of a build in public kind of thing where we are no experts in the fields we're just trying to build stuff. And because streaming is a fun activity, we're trying to learn via doing something fun. Also, I think have very good opinions about streaming as it puts you in a zone and hopefully doesn't let you look at phone, etc. So this is going to be a good learning opportunity and like a flow state for us. The series I want to do personally is like um, even though I had some background is that even though I had a lot of courses in college in deep learning, um, I do not have a good intuition behind how data works and how the architecture works. Like, in what is the secret sauce? Is the secret sauce the data or the architecture, or what is the balance between the two, and which is generally the most important, or not the most? How should it be given a problem? How should I approach a problem? Like, I lack the basic intuition and the understanding behind solving a problem. I've been introduced multiple problems, multiple architectures, and what data is being used in each of them. But given a new problem, I'm not very sure how would you approach a problem with the given data you have, or is the data enough, or like would you want to synthetically create some more, or how do you want to do it, and what would be the best architecture for that data, or for that matter to first also understand how does neural nets store this information inside them, and how do you check whether the training is going well or not. I'm not very great in these aspects of deep learning. This is my stab at learning and growing in this area. So what do I actually want to do now is like I want to uh, go through a set of papers, and then so these are like the papers from the beginning, beginning as in probably not very old, but from attention and other new papers. I just want to spend time implementing each of them, going through, getting my hands dirty, so that I get proper intuition on how these basic building blocks work. And based on that, I'll try to get the feel, as I said. So the first paper is the paper, like very basic paper and groundbreaking paper. Attention is all you need. So I've spent some time recently reading the paper, but again, for sake of completeness, we'll try to do this. Dia is not my primary browser, by the way. Just want to use it so that I want to use this mail ID in my primary browser. Okay, so I think the targets for me for each paper is to uh, implement the paper as is first, and then choose another data set and try the same. Write represent paper as mathematical oh, equations slash write block. These are the three things I want to do for every paper. Probably 3 days per paper. Hopefully. So first we'll try to understand what the paper is. Can I do that? No. Okay, super. So let's start with reading the paper first. The dominant sequence transaction models are based on. I also want to maintain a notes based on what I'm reading so that I can go back to what I've read, and yeah, so I probably would write that in a talks. So I'm not sure what is the best place to write this. mm, Probably let's create markdown is all you need. The dominant sequence transaction models are based on complex, recurrent, or convolutional networks that include an encoder and a decoder. The best performing models also connect the encoder and decoder through an attention mechanism. We propose a simple new architecture, the transformer based solely on attention mechanisms, dispensing with recurrence and convolutions entirely. Experiments in two machine transaction tasks show that these models to be superior in quality while being more parallelizable, requiring significantly less time to train. Our model achieves 28.4 blah 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 on the English German translation task, improving over the existing best results, including an ensembles by over 2 BLE. On the WMT 2014 English to French translation task, a model establishes a new single model state of the art milieu score of 41.3.8 GPU small fraction training cost is the best model in the literature. We show that the transformer generalizes well to other tasks by applying it successfully to English constituency parsing both with large and limited training data. Introduction. Recurrent neural networks, RNNs, short LSTMs, and GRNNs in particular have been firmly established as the state of the art in sequence modeling and transaction problems such as language modeling and machine translation. Numerous efforts have been since continued to push the boundaries of recurrent language models and encoder and decoder architectures. Recurrent models typically factor computation along the symbol positions of the input and output sequences. Aligning the positions to steps in computation time, they generate a sequence of hidden states HT as a function of the previous hidden state HT minus 1 and the input for position T. This inherently sequential nature precludes parallelization within training examples, which becomes critical at longer sequence lengths as memory constraints limit batching limit batching across examples. Recent work has achieved significant improvements in computational efficiency through factorization tricks and conditional computation, while also improving model performance in case of the latter. The fundamental constraint of sequential computation, however, remains. The attention mechanisms have become an integral part of the compelling sequence modeling and transaction models in various tasks, allowing modeling of dependencies without regard to the distance in the input or output sequences. In all but a few cases, however, such attention mechanisms are used in conjunction with a recurrent network. In this work, we propose a transformer, a model architecture eschewing recurrence and instead relying entirely on an attention mechanism to draw global dependencies between input and output. The transformer allows for significantly more parallelization and can reach a new state of the art in translation quality after being trained for as little as 12 hours on 8 P100 GPUs. Background. The goal of the reducing sequential computation also formed the foundation of the extended neural GPU ByteNet ConvS2S, all of which use convolutional neural networks as a basic building block, computing hidden representation in parallel for all input and output positions. Using convolutional CNNs as building block to compute hidden representation for all input and output positions. In these models, the number of operations required to relate signals from two arbitrary input or output positions grows in the distance between positions linearly for ConvS2S and logarithmically for ByteNet. This makes it more difficult to learn dependencies between distant positions. In the transformer, this is reduced to a constant number of positions, albeit at the cost of reduced effective resolution due to averaging attention weighted positions, an effect we counteract with multi-head attention as described in section 3.2. I also want to put this out here so that Self attention, sometimes called intra attention, is an attention mechanism relating different positions of a single sequence in order relating different positions of a single sequence in order to compute a representation of the sequence. Self attention, sometimes called intra attention, is an attention mechanism relating different positions of a single sequence in order to compute a representation of the sequence. Self attention has been used successfully in a variety of tasks, including reading comprehension, abstractive summarization, textual entailment, and learning task independent sentence representations. End to end memory networks based on a recurrent attention mechanism instead of sequence aligned recurrence and have been shown to perform well on simple language question answering and language model tasks. To the best of our knowledge, however, the transformer is the first transaction model relying entirely on self attention to compute representations of its input and output without using sequence aligned RNNs or convolutions. In the following sections, we will describe the transformer, motivate the self attention mechanism, and discuss its advantages over models such as blah blah blah. Okay. Model architecture. The most competitive neural sequence transaction models have an encoder decoder structure. Here, the encoder maps an input sequence of symbol representations to a sequence of continuous representations. I want to write math, and I think I've seen some software. Damn, Twitter doesn't have search for followers. Following. Circa, Corca, something like that. It's circa only. Corca. Collaborative math editor. Yes. I have found the name. Gorka. Funnily enough, these are also discussing some kind of transformers. Ouch. I want this to stay in my account. Let's see. I'll try to copy it later. No, no, no. Ouch. Not sure how to use this. Let's hop into it. The encoder maps the input sequence of symbol representations to a sequence of continuous representations Z. Given Z. Here, the encoder maps an input sequence of symbol representations x1 to xn to a sequence of continuous at a time. At each step, the model is autoregressive, consuming the previously generated symbols as additional input when generating the next. The transformer follows this overall architecture with stacked self-attention and point-wise fully connected layers for both encoder and decoder. Encoder and decoder stacks. The encoder is composed of a stack of n equals 6 identical layers. Each layer has two sublayers. The first is a multi-head self-attention mechanism. The encoder is composed of stack of n equals 6 identical layers. Each layer has two sublayers. The first is a multi-head self-attention mechanism. Each layer has two sublayers. First is a multi-head self-attention mechanism, and the second is a simple position-wise fully connected feed-forward network. We employ a residual connection around each of the two layers. So there are 6 identical layers. Each layer has two sublayers. One is multi-head self-attention mechanism, and the second is a simple position-wise fully connected feed-forward network. We employ a residual connection around each of the two sublayers, followed by the layer norm. That is, the output of each sublayer is layer norm x plus sublayer x, where sublayer x is a function implemented by the sublayer itself, and x is the residual connection. To facilitate these residual connections, all sublayers in the model, as well as the embedding layers, produce outputs of dimension D model 512. Decoder is also composed of stack of n equals 6 identical layers. In addition to the two sublayers in each encoder layer, the decoder inserts a third sublayer which performs a multi-head attention over the output of the encoder stack. Similar to the encoder, we employ residual connections around each of the sublayers followed by the layer norm. We also modify self-attention sublayer in the decoder stack to prevent positions from attending to subsequent positions. This masking, combined with the fact that output embeddings are offset by one position, ensures that the predictions for position I can depend only on the known outputs at position less than I. The decoder is also composed of a stack of n equals 6 identical layers. In addition to the two sublayers in each encoder layer, the decoder inserts a third sublayer which performs multi-head attention over the output of the encoder stack. Similar to the encoder, we employ residual connections around each of the sublayer followed by layer norm. We also modify the self-attention sublayer in the decoder stack to prevent positions from attending to subsequent positions. This masking, combined with the fact that output embeddings are offset by one position, ensures that the predictions for position I can depend only on the known outputs at positions less than I. Attention. An attention function can be described as a mapping a query and a set of key value pairs to an output. An attention function can be described as a mapping a query and of a set of key value pairs to an output where the query keys and values output are all vectors. The output is a weighted sum of the values where the weight assigned to each value is computed by a compatibility function of the query with the corresponding key. Let's do it together next time. Scale dot product attention. We call a particular attention scale dot product attention. The input consists of queries and keys of dimension dk and values of dimension dv. So there are queries of dimension dk and keys of dimension a. Okay, yeah. Keys are also called dimension dv because I think keys and values should be of same size, maybe. We compute the dot products of the queries with all keys. We compute dot products of query with all keys and divide each of them by under root dk and apply a softmax function to obtain the weights on the values. Another to do is understand properly y divided by root dk. The two So in practice, we compute the attention function on a set of queries simultaneously packed together into a matrix Q. The keys and values are also packed together into matrices K and V. We compute the matrix of outputs as attention Q K V is softmax of Q K transpose divided by under root dk scalar times value matrix. The two most commonly used attention functions are additive attention, the dot product attention. Dot product attention is identical to our algorithm except for the scaling factor of under root dk. The additive attention computes the compatibility function using a feed forward network with a single hidden layer. While the two are similar in theoretical complexity, the dot product attention is much faster and more space efficient in practice since it can be implemented using highly optimized matrix multiplication code. I should also try to understand this. While for small values of decay, the two mechanisms perform similarly, additive attention outperforms dot product attention without scaling for larger values of decay. We suspect that for large values of decay, the dot product grows large in magnitude, pushing the softmax into regions where it has extremely small gradients. To counteract this effect, we scale the dot products by under root decay. First, I'm trying to go through this thing and again come back and write notes entirely. While for multi-head attention, instead of performing a single attention function with D model dimensional keys, values and queries, we found it beneficial to linearly project the queries instead of performing a single attention function with three model dimensional keys, values and queries. We found it beneficial to linearly project the queries, keys and values h times with different learned linear projections to dk, and dv dimensions respectively. On each of the projected versions of queries, keys and values, we then perform the attention function in parallel, yielding dv dimensional output values. These are concatenated and once again projected, resulting in final values as depicted in figure 2. Multi-head attention allows a model to jointly attend to information from different representation subspaces at different positions. With a single attention head, averaging inhibits this. Where the projections are parameter matrices Wi query D model cross dk. D model, where D model is the input embedding size times the size is the key vector. So WIQ, WIK and WIV and WO is what? Okay, is multiplied to the concatenated heads. In this work, we employ h equals 8 parallel attention layers or heads. For each of these, we use dk equals dv equals d model by h equals 64. Due to reduced dimension of each head, the total computational cost is similar to that of single head attention with full dimensionality. Applications of attention in our model. The transformer uses multi-head attention in three different ways. In encoder decoder attention layers, the queries come from the previous decoder layer. The queries come from the previous decoder layer, and the memory keys and values come from the output of the encoder. The query comes from the decoder layer, key and value come from the output of the encoder. This allows every position in the decoder to attend over all positions in the input sequence. This mimics a typical encoder-decoder attention mechanisms in sequence-to-sequence models such as something. The decoder contains self-attention layer. The encoder contains self-attention layer. I also decoded. In a self-attention layer of all of the keys, values and queries come from the same place. In this case, the output of the previous layer in the encoder. Each position in the encoder can attend to all positions in the previous layer of the encoder. Similarly, self-attention layers in the decoder allow each position in the decoder to attend to all positions in the decoder up to and including that position. We need to prevent leftward information flow in the decoder to preserve the autoregressive property. We implement this inside of scale dot product attention by masking out, setting to infinity, all values in the input of the softmax which correspond to illegal connections. Position-wise feed-forward networks. In addition to attention sublayers, each of the layers in our encoder and decoder contains a fully connected feed-forward network, which is applied to each position separately and identically. In addition to attention sublayers, each of the layers in our encoder and decoder contains a fully connected feed-forward network. It consists of two linear transformations with the ReLU activation in between. FFN x equals max of 0 x times w1 plus b1 ReLU over the first layer and scaling and the linear transformation again. While the linear transformations are the same across different positions, they use different parameters from layer to layer. Another way of describing this is as two convolutions with kernel size 1. The dimensionality of input and output is D model 512. Excuse me. And the inner layer has dimensionality DFF equals 2048. Embeddings and softmax. Similarly to the other sequence transaction models, we use learned embeddings to convert the input tokens and output tokens to vectors of dimension D model. Similar to other sequence transaction model, we use learned embeddings to convert the input tokens and output tokens to vectors of dimension D model. We also use a usual learned linear transformation and softmax function to convert the decoder output to predicted next token probabilities. In our model, we share the same weight matrix between the two embedding layers and the pre-softmax linear transformation similar to this paper. In the embedding layers, why is this working? Complexity per layer of self-attention is O n square D. Why is it O n square D? Hmm. The most the most complicated or the most compute intensive part of this is the multiplying the query and the key matrices, as far as I understand. And each so q the q matrix is of the shape n cross d, and k matrix is of the shape d cross n, right? So we have to take a dot product of the query vector, which is of the size d cross 1, n. So a dot products of the complexity of the complexity of dot product between two vectors of size d cross 1 is d, right? And we're doing this n square times. That is, we have n query vectors, we have n key vectors, and we multiply each query vector with each key vector. So n cross n. This is n square times dot product, which is of complexity d. So the complexity per layer is n square d. And because each of them